Okay, thank you for the introduction and for attending this talk. In our work, we focus on serverless and in particular on cold start, where a client sends a request to a server that needs to answer to this request. To do so, the server creates a new process that needs to execute the code associated with the request. This code, however, is initially not located in memory and thus needs to be fetched either from the storage or from the network. After fetching and executing this code, the server can execute it and send back the response to the client. Subsequent requests are much faster since the code is already located in memory and the process does not need to be created since it's already running. The problem is that cloud computing services typically retain the execution environment only for a certain and limited period of time, after which idle programs are removed. And this is to allocate resources to other processes. Cloud computing services would like to do it as soon as possible. In this sense, it's crucial to improve cold start performance. In our work, we focus on GraalVM Native Image. That is a predominant technology used in main cloud computing infrastructures. GraalVM Native Image allows creating binary files from Java application by compiling the Java code, leveraging the Graal compiler when used as ahead-of-time compiler. These binaries can be executed without the need of instantiating a Java virtual machine and also contain a snapshot of the pre-initialized Java heap memory to further speed up the startup. Our goal is improving the spatial locality of the objects stored in this snapshot to reduce page faults and thence reduce the associated I/O traffic. I would like to list here the contributions of our work. First, we propose an approach to map semantically equivalent objects in different binaries of the same application. To do so, we propose the concept of Context-Augmented Heap-Path. In particular, we match CAHPs, Context-Augmented Heap-Paths of objects. First, exactly, and then we propose a partial path matching algorithm that allows to match more objects. And this exploits a similarity metric for CAHPs. We then integrate our approach in Native Image, and we evaluate its performance. Here we can see a simple example. Java code consists of a main class that defines a main method. The main method here simply checks whether the user provides a -v option. In such a case, the program prints on the started error the current application version stored in the version field of type pair by using the version string method defined below. In this example, we consider only method main, method version string, and the 3 objects of type pair and the 2 integers. On the right-hand side of this slide, you can see a native image binary produced by the default native image implementation. Here you can see different cells. Each cell represents a page of the binary. You can see 2 sections, the text section and the SVM heap section that contains the snapshot of the heap. In particular, you can see that the 2 methods are located in the first page of the text section, while the 3 objects we consider are located in 2 different pages of the SVM heap section instead. If we execute this program by providing the -v option, we encounter 3 different page faults, 1 to the text section and 2 to the heap sections. Our goal is compacting the accessed objects in fewer pages to reduce the total number of page faults. In this case, we get 2 page faults in total. In this slide, I show a visual representation of a native image binary, in particular the baseline and its optimized version, to show the effectiveness of our approach. We focus on the SVM heap section here. Here, each cell represents a page of the binary, and we focus in particular on the green cells that represent pages that caused page faults. As you can see, typically, only a small percentage of the objects in the heap snapshot is accessed, and our technique is effective in reducing this number of green cells and thence page faults. We do so by changing the layout of native image binaries during compilation. And we do it by extending existing profiles collected by instrumented native image binaries, and we use these extended profiles to generate the optimized binary with the new layout. We generate the instrumented binary by leveraging event tracing profiler and minting also some metadata. We then collect a method invocation trace and an object access trace by executing the instrumented binary, and we use these traces in the optimized image build process to perform the optimizations, which is storing methods and objects based on their first invocation and access, respectively. The issue in this workflow, so in profile-driven heap layouting, is that this process requires mapping objects in the optimized binary to the semantically equivalent objects in the instrumented binary, and thence the objects that appear in the trace. This is challenging for two main reasons. First, objects do not have a unique identifier that is stable across builds, and second, the Heap-Snapshot contents are not guaranteed to be the same across builds. This is for several reasons. For example, non-determinism in running crash initializers, non-determinism in the JDK, profiler that influences the contents of the binary, or different compilation decisions. For example, different inlining decisions across builds, of course. So our problem becomes matching two different heap object graphs. We simplify this problem by comparing single paths from roots to individual objects. Let's consider again our example Java code, and in particular the case where the pair instance is constant folded into the main method. This produces simplified heap object graphs that looks like this. So we have a pair and two integers as children. We identify the pair instance using the path consisting of the pair itself, the integer in the left field using this path, and the integer in the right field using this other path. The reason is that in this way we can match objects by considering only some of their ancestors and not their siblings or children, and hence we do not need to consider divergences between the entire neighborhoods of the node when we try to match them. Moreover, this allows us also to match semantically equivalent objects that are associated, however, to different paths across builds by computing a similarity factor for these paths. In particular, we perform only a best effort matching, which means that we match each object in the optimized image with one object in the instrumented image. To do so, we use two matching algorithms. First, an exact match, and then a partial path match that we propose. And this is to mitigate the issues that we presented before. We would like to note that mismatches reduce only the effectiveness of the optimizations and thus performance, but do not impair the correctness. And this is because we modify only the serialized representation of the heap object graph, but we do not modify the heap object graph itself. Due to a matter of time, we would like to explain here on the CAHP generation step. The goal of this step is representing each object by creating a list of elements that describes it. This list of elements is in practice our CAHP that is used to better identify the semantically equivalent objects in two different builds of the same program. Let's consider, for example, this path representing the integer in the left field. The corresponding CAHP is reported on the right-hand side of this slide. As you can see, we have a main method. In this main method, a pair is constant folded into this main method. This pair contains a left field that stores an object of type integer that encapsulates value 7. Before concluding, I would like to present here our evaluation results. We conduct our experiments using a modified GraalVM Community Edition based on OpenJDK 21. In particular, we build statically linked executable from the RWFastYet benchmark suite to evaluate the speed up on short-running programs, often used in the Function-as-a-Service model, and on Hello World implemented with popular microservice frameworks. This is to evaluate the speed ups on the serverless model when using long-running processes. We use Hello World because we want to evaluate the performance on the frameworks and not on the user application, which evaluate with the RWFastYet benchmark suite. In terms of metrics, we evaluate page fault reduction factors using perf and performance, in particular in the execution time, end-to-end time for RWFastYet, and time to first response for microservices. We evaluate different ordering strategies, namely code and heap, where we order only code and heap respectively, and code plus heap, where we order both together. In this plot, you can see the page fault reductions factors achieved by our technique. On the y-axis, the higher the better. On the x-axis, you can see the benchmarks, RWFastYet up to towers, and then microservices. Different columns represent different ordering strategies. Overall, we see that heap ordering leads to higher reduction than code ordering, and then code and heap ordering are synergistics. Code and heap are not independent, but the heap is laid out based on the code, as also the accesses on the heap depends on the ordering of the code. And the heap also represents some metadata related to the code. So there is an interconnection here. We can see that we have a geometric mean reduction of 3.14 for our fast yet, 2.72 for microservices, and 2.98 in total. Here we report the execution time speed of factors instead that mostly correlate with page fault reductions with some exceptions. In particular, on microservices, we have higher speedups for code and heap. We have a geometric mean of 2.0 for our fast yet, 1.92 for microservices, and 1.98 in total. To conclude, we propose the new concept of context-augmented heap-path that we use to match semantically equivalent objects in different binaries of the same application. In particular, we use an exact matching and a partial path matching that we propose. You can find the details in the paper that we have not presented here due to time. We integrated our approach in native image, and we evaluated it on our fast yet and on popular microservice frameworks, showing a page fault reduction factor of 2.98 on average and 1.98 average speed up. I would like to thank you for your attention, and I would be glad to answer your questions.
There have been attempts in the past to derive the information that you do statically. So it's quite interesting because they all have, in my opinion, failed for languages like this. So it's very interesting to see your effort based on native image. The question I have is, you mentioned code and heap and code plus heap in your evaluation. So what do you mean by code ordering, and do you mean that you also change the order in which basic blocks are laid out or so on? What is it?
No, at the moment we order only the compilation units, so like methods based on their executions. We do not reorder the basic blocks within the compilation units, though.
Okay, so if two compilation units are brought together, it's likely that the objects referenced there are also brought together. Is that the case in code plus heap?
In code plus heap, we order the code section, so the compilation units, and then we order the objects in the heap.
Okay. Yeah. Okay. I'll talk more offline on that as well. Thanks.
One more very quick question. No? One from me. Now that you looked at page faults, is the next step looking at kind of cache line granularity to maybe even squeeze more time out of it?
So the next step would be actually to look at to reorder not only maybe objects, but also the layout within the same objects or the basic blocking indeed within the same compilation units. Because at the moment we have, for example, if you look at the visualization, you see that we have huge arrays, for example, containing native image metadata. We order only these arrays, putting them one after the other. The issue is that we do not order the elements within the arrays, so we have page faults that are caused by accessing single objects located in different pages. So we were thinking about, instead of cache lines, we were thinking about further reducing page faults by looking at the finer granularity in that sense.
Okay, cool. Thank you very much.
Thank you.
Let's thank Matteo.